Here are trivia about the 10 elements you can listen to in English. Now, let's get started.
Radioactive watch dials. Did you know that the alluring glow of some early 20th century watches was powered by a highly radioactive element? In that era, a special luminous paint containing radium-226 was widely applied to watch dials and hands. The mechanism involved alpha particles, continuously emitted by the radium, striking a fluorescent material in the paint, causing it to luminesce. With an immense half-life of 1,600 years, the radium provided a long-lasting glow, but also a persistent and dangerous source of radiation. The tragic story of the Radium Girls highlights these dangers. These female factory workers, tasked with painting the dials, ingested fatal amounts of radium by habitually licking their brush tips to maintain a fine point, leading to horrific health consequences such as jaw necrosis and bone cancer. The suffering of the Radium Girls, however, was not entirely in vain, as their court cases were pivotal in establishing occupational disease labor laws and improving industrial safety standards. Following this tragedy and the growing awareness of its dangers, radium was eventually phased out of consumer products. It was succeeded by significantly safer alternatives, initially tritium, which emits less penetrating radiation, and more recently by modern non-radioactive photoluminescent materials. Today, these vintage radium timepieces are treated as hazardous collectibles, as the decaying radium can produce radon gas, posing a significant health risk if the watch case is ever opened or compromised. Hand-melting metal. Have you ever seen a solid metal liquefy in the palm of a hand? This is a reality with gallium, a metal with an extraordinarily low melting point of just 29.76 degrees Celsius. This temperature is low enough for the warmth of human skin to turn a solid piece of gallium into a liquid pool. The reason for this peculiar property lies not in its elemental composition, but in its unique crystal structure. The bonds between the gallium atoms in its solid state are unusually weak, requiring very little thermal energy to break apart and allow the metal to transition into a liquid phase. Unlike most metals, which form a tightly packed crystal lattice, solid gallium structure is composed of Ga2 dimers, where pairs of atoms are strongly bonded together, much like a molecule. The key to its low melting point is that the bonds between these dimers are significantly weaker and more easily overcome. Consequently, it is the breaking of these weak interdimer connections rather than the strong bonds within the dimers themselves that causes the metal to melt at such a low temperature, a characteristic that sets it apart from other metallic elements. Gallium's corrosive trick. Can a safe, non-toxic metal cause another sturdy metal to disintegrate in water? Gallium, a metal with a melting point of only 29.8 degrees Celsius, does exactly that when it comes into contact with aluminum. On its own, gallium is unreactive in water because a stable passivation film of gallium oxide forms on its surface, preventing further reaction. However, when alloyed with aluminum, its properties change dramatically. The gallium disrupts the formation of aluminum's own protective oxide layer, which normally makes it resistant to corrosion. This disruption exposes the raw aluminum directly to water, triggering a vigorous chemical reaction. The aluminum-gallium alloy reacts with water to rapidly produce hydrogen gas and aluminum hydroxide, causing the solid aluminum structure to crumble and fall apart. Technically, the gallium is not consumed in the reaction. It acts as an enabler for the aluminum's inherent reactivity with water. This process is a form of liquid metal embrittlement, and due to this ability to compromise aluminum alloys, gallium is classified as a hazardous material and is heavily restricted on aircraft. Sodium's Coulomb Explosion. Why does pure sodium explode so violently upon contact with water? The reaction of just 1 gram of sodium with water generates approximately 0.5 liters of hydrogen gas and significant heat, leading to ignition. The chemical process is described as 2Na plus 2H2O, right-pointing arrow, 2 sodium hydroxide plus H2 plus heat. However, the sheer speed of this reaction is explained by a theory known as the Coulomb Explosion. According to this model, as soon as sodium metal touches water, it rapidly releases electrons. This leaves the remaining sodium atoms as a cluster of positively charged ions that, due to intense electrostatic repulsion, fly apart with explosive force. This modern theory provides a more complete picture than the traditional explanation, which simply attributed the explosion to the heat of the reaction igniting the hydrogen gas. That older model fails to account for the incredible speed at which the metal initially fragments, often faster than sufficient heat can build up. The Coulomb explosion explains this initial rapid dispersal. By violently shattering the metal into a fine mist, it massively increases the surface area available for the chemical reaction. This allows the subsequent production of hydrogen and heat to occur almost instantaneously, resulting in the powerful blast observed. Sun's slow light. Did you know that the sun loses 4.26 million metric tons of mass every single second? Our star is a colossal nuclear fusion reactor, and in its core, approximately 600 million metric tons of hydrogen are converted into helium every second. During this process, a portion of the mass is not carried over, but is transformed directly into a tremendous amount of energy, precisely following Albert Einstein's famous equation, E equals mc squared. This constant conversion of mass into energy is what has powered our solar system for billions of years. However, the light generated from this fusion does not reach us immediately. The journey of a photon from the sun's core to its surface is an extraordinarily long and arduous one. A photon must travel through the incredibly dense radiative zone, where it is continuously absorbed and re-emitted in a random path. This random walk can take anywhere from 10,000 to 170,000 years. Only after finally emerging from this zone and passing through the convective layer can it escape into space, beginning its much quicker 8-minute and 20-second journey to Earth. Explosive cesium. Can you imagine a metal so reactive that it explodes on contact with ice at a temperature of -116 degrees Celsius? This is the reality for cesium, the most reactive of all alkali metals. Its extreme reactivity stems from its position at the bottom of group 1 in the periodic table. As you move down this group, the atomic radius of the elements increases. For cesium, this means its outermost valence electron is located far from the nucleus and is very loosely held, making it exceptionally easy to lose in a chemical reaction. This tendency to readily give up an electron is what fuels its violent reactions, even with substances as cold as solid ice. Due to this incredible reactivity, cesium is never found in its pure elemental form in nature. It would instantly react with moisture or oxygen in the air. Instead, it exists only within compounds in minerals, such as pollucite. To obtain pure cesium metal, a process of isolating it from these compounds is necessary. The primary method used for this separation is electrolysis, which uses an electric current to drive a non-spontaneous chemical reaction and extract the highly reactive metal from its more stable mineral form. Strongest permanent magnet. Have you ever wondered what makes the small, silvery magnets used in modern electronics so incredibly powerful? The secret behind the formidable strength of neodymium magnets with the chemical formula Nd2MuLTIVAN Fe14B1 lies not just in their composition, but in their unique atomic arrangement. These magnets possess a specific tetragonal crystal structure. This highly ordered microscopic lattice rigidly locks the magnetic orientation of the individual atoms, forcing them to align perfectly in the same direction. This unified alignment generates an exceptionally strong and concentrated magnetic field, far exceeding that of older magnet types. This property is technically known as magnetic anisotropy, and it is extremely high in this material. Magnetic anisotropy describes the crystal's preference for magnetization along a specific direction, often called an easy axis. Within the Nd2MuLTIVAN structure, the large neodymium atoms play a crucial anchoring role. They effectively pin the magnetic alignment of the iron atoms, which are the primary source of the magnetism, preventing it from being easily scrambled by external magnetic fields or thermal energy. This structural stability is what gives neodymium magnets their remarkable and lasting power. Empty atom, dense core. Imagine a sugar cube weighing more than all of humanity. While an atom consists mostly of empty space, its core, the nucleus, is extraordinarily dense, reaching about 2.3 by 10 to the power of 14 grams per cc. To put this into perspective, if you could pack a 1 cubic centimeter sugar cube with this nuclear material, its mass would be approximately 230 trillion kilograms. This single cube would vastly exceed the combined weight of all 8 billion people currently living on Earth. This incredible density is a result of the strong nuclear force, one of the 4 fundamental forces of nature. This force is immensely more powerful than the electromagnetic force, allowing it to overcome the intense repulsion between positively charged protons and bind them, along with neutrons, into an incredibly small volume. Interestingly, this state of matter is not just theoretical. A neutron star, the collapsed core of a massive star, is a celestial object that possesses a density comparable to that of an atomic nucleus. Mass from energy. Have you ever considered where the mass of ordinary matter truly originates? The surprising answer is that most of it comes not from particles, but from pure energy. While atoms are mostly empty space, the vast majority of their mass is concentrated in the protons and neutrons within the nucleus. These particles are composed of smaller fundamental particles called quarks. However, the mass of a proton is not simply the sum of its constituent quarks. In fact, approximately 99% of a proton's mass is derived from the immense energy of the strong interaction that binds the quarks together. This binding energy manifests as mass according to Albert Einstein's famous equation E equals mc squared. To put this into perspective, the combined mass of the 3 constituent quarks inside a proton accounts for only about 1% of the particle's total measured mass. The remaining 99% is the mass equivalent of the kinetic energy of the quarks zipping around and the potential energy of the powerful gluon field that confines them. This discovery fundamentally challenges our everyday notion of mass as the amount of stuff in an object. It reveals that at the subatomic level, mass is a dynamic property emerging from the interplay of fundamental forces and energy, a profound consequence of modern physics. Fireworks color chemistry. Have you ever wondered how fireworks produce their vibrant and diverse colors? The brilliant spectacle is a direct result of chemistry, specifically the flame tests of different metal elements. Each color is created by adding a specific metallic salt to the pyrotechnic composition. For instance, the deep crimson red that illuminates the sky is produced by strontium, which emits light in the 640 to 750 nanometer wavelength range. A vivid blue-green color, on the other hand, is achieved by using copper compounds, typically copper chloride. This colorful phenomenon is based on the principle of atomic emission. When the firework explodes, the intense heat excites the electrons within the metal atoms, forcing them to jump to higher energy levels. As these electrons fall back to their original, stable ground state, they release the excess energy in the form of light. The specific wavelength, and thus the color of the light, is unique to each element. While this principle is a powerful tool for qualitative analysis to identify the presence of certain elements, it is generally not suitable for quantitative analysis to determine their precise amounts.